So the first thing I want to go over, I sent an email about this. Abstract Algebra is being offered by Dr. Lipson. Here's the information. You should have also received it in an email. It's going to start September 9th, so please be sure to email him as soon as possible if you are interested. Today we're going to do section 1.1, Systems of Linear Equations. A linear equation. Linear equation is in the form of ax1 plus ax2 plus all the way to a and xn equals b. So our x's are our unknowns. Example 1, find the linear equation. So we have 4x1 minus 5x2 plus 2 equals x1. So go ahead and try to find that linear equation. So what we would do is we subtract x1 from both sides and subtract 2 from both sides. So we would have 3x1 minus 5x2 equals negative 2. Let's look at b. x2 equals 2 times the square root of 6 minus x1 plus x3. So first you'd want to distribute your 2 through. So we'd have x2 equals 2 square root of 6 minus 2x1 plus x3. Then you would want to get x's on one side and your variable, your constant on the other side. So I'm going to add 2x1 to both sides and subtract x3. So I would have 2x1 plus x2 minus x3 equals 2 square root of 6. And some nonlinear examples would be something like 4x1 minus 6x2 equals x1 times x2. Or something like x2 equals 2 times the square root of x1 minus 7. System of linear equations, or also known as a linear system, is a collection of one or more linear equations involving the same set of variables, say x1, x2, all the way to xn. A solution of a linear system is a list, s1, s2, all the way to sn, of numbers that make each equation in the system true when the values s1, s2, and sn are substituted for x1, x2, and xn respectively. So let's look at two equations in two variables. First, we have two lines intersecting, and these have the equations x1 plus x2 equals 10 and negative x1 plus x2 equals 0. This has one unique solution of 5, 5. Next, let's look at these two lines. They have the equations x1 minus 2x2 equals negative 3, and 2x1 minus 4x2 equals 8. This has no solution, since the lines will never intersect. And then the last one, we have x1 plus x2 equals 3, minus 2x1 minus 2x2 equals negative 6. Infinite many solutions because both of these lines are the same. They are on top of each other. Let's look at some basic facts. So a system of linear equations has either one exact solution, which is consistent, also known as consistent, infinitely many solutions, also known as consistent, or no solution, which is inconsistent. So when we're asking if a system is consistent, you're seeing if it has solutions. Consistent has one or infinitely many solutions. So remember that, and inconsistent has no solutions. Solution set. The set of all possible solutions to a linear system. And equivalent systems is two linear systems with the same solution set. Solve the system. So I have this system of equations, x1 minus 2x2 equals -1, and -x1 plus 3x2 equals 3. So the first thing I could do, I noticed that if I add these together, these would cancel out, this would become x2, and I would have x2 equals 2. Okay? And then I can solve for x1 by taking x1 minus 2x2 equals -1. I can either plug it in, or again, I know that positive 2x2 equals 4. So I would get x1 equals 3. So my solution would be x1 equals 3 and x2 equals 2. Another way we can do this is we can use an augmented matrix, which is what we're going to use for the most part in this class. So I could go ahead and write my matrix 1, -2, -1, and then -1, 3, 3. And I could go ahead, this is known as row 1. So when I talk about rows, just to review, this is row 1, this is row 2. I could go ahead and I'm going to leave the top row how it is, because what you want to do is you want to create a 1 here, a 0 here, a 0 here, and a 1 here, because this first column corresponds to x1. The second column corresponds to x2. So when I solve for it, I'd have 1 equal in whatever number I get here. So since this is already 1, I'm going to leave it alone. I notice if I add row 1 to row 2, I'd get a 0 here, and that's what I want. So I'm just going to add row 1 and row 2. And if you look here, this corresponds to x2. x2 equals 2. So we went ahead and already solved for that one. Now we need to get this to become a 0. And in order to do that, all we have to do is take twice of row 2 and add it to row 1. So if I take twice of row 2 and add it to row 1, I'd get 1, 0, 3. And I didn't do anything to my second row, so that would stay like this. And there I have x1 equals 3 and x2 equals 2. So let's look at 3 equations and 3 variables. Let's talk about them. So this first one, the planes intersect at one point, so we would only have one solution. In this next picture, the planes intersect in one line, so we would have infinitely many solutions. In this last one, the planes there's no common point to all 3 planes, so there would be no solution. So those are visuals of what it would look like when we are dealing with 3 equations in 3 variables. So how we would go about solving these are through elementary row operations. So a lot of this you already know. So first is replacement, add one row to a multiple of another row. Interchange, so we can interchange 2 rows. And scaling, multiplying all entries by a non-zero constant. So those are the things you can do. Row equivalent matrices are 2 matrices where one matrix can be transformed into the other matrix by a sequence of elementary row operations. And facts about row equivalence: if the augmented matrix of 2 linear systems are row equivalent, then the 2 systems have the same solution set. So let's look at example 3. Solve the following system. So we're going to go ahead and solve the system just using matrices. So go ahead and write your matrix. So this would be 1, -2, 1, 0. And then 0, 2, -8, 8. And -4, 5, 9, -9. So usually when I go ahead and do matrices, I go straight down, and then when I run out of room, I'll come back over here. So this is equivalent to, so what I'm going to do is I'm going to take 4 times row 1 and multiply it and add it to row 3. Because I already have a 0 here, I want to try to get this to be a 0. So I'm going to take 4 times row 1 and add it to row 3. So row 1 is going to stay the same. Row 2 is staying the same. And 4 times row 1 plus row 3 would give me 0, -3, 13, and -9. The next step, I notice I want this to become a 1. So I want this right here to become a 1. All I have to do is half this whole row, and it becomes a 1. So first row, I'm not doing anything to again. So 1, -2, 1, 0, 0, 1, -4, 4, and 0, -3, 13, -9. So next I notice if I take 3 of row 3 or 3 of row 2 and add it to row 3, I would get a 1 here. And that's my goal. I also want to have a 1 there. So I'm going to go ahead and do that and multiply row 2 by 3 and add it to row 3. So I still haven't done anything to row 1. Row 2, I'm not doing anything to. I'm going to change row 3 by multiplying row 2 by 3 and adding it to row 3. So I'd get 0, 0, 1, and 3, I believe. Now I'm just going to go ahead and come up here. So the next step, I'm going to do 2 steps at once, and you can do this all the time. I'm going to take negative of row 3 and add it to row 1 so that I can get this to become a 0. I'm also going to take 4 of row 3 and add it to row 2, so this will become a 0 because I want zeros all above this 1 so that I can have a solution. So when I do that, row 1 becomes 1, -2, 0, -3, and I got that by taking negative row 3, adding it to row 1. And now I'm going to take 4 times row 3 and add it to row 2, and I'd get 0, 1, 0, 16. And row 3 is just 0, 0, 1, 3. The last thing I need to do is this has to become a 0. So I can take 2 times row 2, add it to row 1, and that would become a 0. So I'd have 1, 0, 0, 29. I have 0, 1, 0, 16, and then 0, 0, 1, 3. So my solution would be 29, 16, 3. And you can go ahead and check that by plugging these values into x1, x2, and x3. And you should get the correct answers from the example. Let's go ahead and look at example 4. Determine if the following system is consistent. So I have x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, and negative 4x1 plus 5x2 plus 9x3 equals negative 9. 2 questions. Is the system consistent? So does a solution exist? If the solution exists, is it unique? One and only one solution. So if you notice, this is the same as our last problem. So based on this last example, the system was reduced to triangular form. So if I stopped, so if you notice at one point in time, this could be reduced to triangular form. At one point, let me make this look a little better. So at one point, we got it down to 1, -2, 1, 0, 0, 1, -4, 4, and then 0, 0, 1, 3. Okay, so this right here, when I have ones across the diagonal, because right here, this is on this side, the coefficient matrix, this is triangular form, okay? And it's upper triangular because all the entries above the diagonal are above the diagonal. So all my entries are above the diagonal. So based on this last example, the system was reduced to triangular form at one point. And the system is consistent and unique because x2 is uniquely determined by equation 2. Okay, so this system is consistent and unique because x2 is uniquely determined by equation 2, since x3 has only one unique solution. Therefore, x1 is determined by equation 1, is what you could say. So you don't have to go through and actually find the solution. You could if they're asking for the solution, but they just wanted us to determine if the following system was consistent. And the following system is consistent because we got it in upper triangular form. And x2 is uniquely determined by equation 2 since x3 has only one unique solution. And therefore, x1 is determined by equation 1. So it has a unique solution. Let's look at example 5. Is this system consistent? So I have 3x2 minus 6x3 equals 8. x1 minus 2x2 plus 3x3 equals negative 1. And 5x1 minus 7x2 plus 9x3 equals 0. So let's go ahead and draw our augmented matrix. So I have 0, 3, negative 6, 8, 1, negative 2, 3, negative 1, 5, negative 7, 9, 0. So what we want to do is try to get this in upper triangular form. And if we get our diagonal of all ones, we'll be able to tell if it's consistent or not. If we can't, then it's probably not consistent. So let's go ahead. I'm going to interchange row 1 and row 2 so that this lead in 1 is on the top. So that's the first thing I'm going to do. I also am going to multiply row 2 by negative 5 and add it to row 3 so I can also get a 0 there. So I would have 1, negative 2, 3, negative 1. I'd have 0, 3, negative 6, 8. And then again, I'm multiplying my original row 2 by negative 5 and adding it to row 3. And I get 0, 3, negative 6, 5. Now I'm going to take negative row 2 and add it to row 3. So I'm going to take negative row 2 and add it to row 3. So my top row, I'm not doing anything to, negative 1, 2, 3, negative 1. My second row, I'm not doing anything to, but I'm taking negative of my second row, adding it to my third row, and I'd get 0, 0, 0, negative 3. So when I get that, right here, 0 can never equal negative 3. I have to have a 1 there. So therefore, the original system is inconsistent because 0 can never equal negative 3. And then example 6, for what values of h will the following system be consistent? 3x1 minus 9x2 equals 4, and negative 2x1 plus 6x2 equals h. So there's many ways that we can do this problem and all the other problems I did. Just as long as you get to the same solution, it's fine. So what I'm going to do is I'm going to set up my augmented matrix. And the first thing I'm going to do is I'm going to divide my first row by 3 so that this will become a 1. So I have 1, -3, 4/3. And my second row, I'm not doing anything to yet. Then I'm going to take twice my first row and add it to my second row. So twice my first row, add it to my second row, and I would get 0, 0, h plus 8/3. So here I have 0 equals h plus 8/3. So I'd just solve for that, and I'd have -8/3 equals h. So my constant, -8/3, which is h, would make the system consistent.